Ladies and gentlemen, I'm Huachun Wu from Wuhan University of Technology, China. I will be talking about online unbalanced vibration suppression of the flexible rotor supported by active magnetic bearing. This slide shows the outline of presentation. First, I will introduce background and objective. Next, I will explain the experimental setup. Then, I will describe the theory and solution approach. After that, I will show you the result and discussions. Finally, I will make a conclusion. First, I will introduce the introduction. Nowadays, the rotating machine has gradually developed from past low power, low efficiency, and low speed to modern high speed, high precision, and high efficiency. At the same time, the performance requirements of the rotating machinery are becoming higher and higher, mainly in high speed. Active magnetic bearing, which has no mechanical contact between rotor and state, can be found in some industry applications such as high-speed rotor and turbomolecular pumps. Example. However, due to uneven material processing accuracy, assembly errors, and other reasons, rotating machinery always has a certain unbalance. Even with very precise mission of rotor parts, it is difficult to avoid the mass unbalance. Especially, large unbalance is typically responsible for high energy vibration and the consequent decrease in machine life. So, unbalanced compensation on the rotor machine is necessary, especially for the high-speed flexible rotor. Generally, the rotor is spinning around its geometrical axis or its inertial axis, so they have to control mass, which are the unbalanced compensation and automation balance, while the unbalanced vibration suppression needs shutdown and phase sensor. How to solve the problem of the online suppressed unbalanced vibration without adding additional hardware equipment in active magnetic bearing rotor system. The testing apparatus for this investigation, the experiment device, is shown in this figure. Now, I will introduce theory and solution approach. The first principle of the cross correlation mass. The initial vibration signal caused by displacement sensor not only contains the fundamental frequency component, but also includes a high-order harmonic, random noise, DC component, etc. Set initial vibration signal as this equation, where X0 represents DC component, NT represents random noise, A0 sin 2 pi F0t plus C0 is the fundamental frequency component. The principle of the cross correlation analysis mass is shown as following. We can get amplify and phase. Here, we will talk about principles of the influence coefficient mass. This mass was adopted to calculate the value of the unbalanced compensation. The key of the influence coefficient mass is to determine the influence coefficient matrix. The input of the system is the trial weight put on the correction plans. The output is the variation of the fundamental frequency signal of the rigid rotor and the same condition. The transitive relationship of the input and output is the influence coefficient of the rotor system. By solving the vector equation, the compensation water signal that should be at on the balancing plane and can be obtained respectively. Now, we talk about principle of the online unbalanced vibration suppression. The compensation water signal obtained by above formulation is the compensation signal of the equivalent unbalanced interference water signal with equal amplitude and opposite phase. From the above analysis, it can be seen that when influence coefficient mass based on the magnetic bearing is used to compensate for the unbalanced vibration of the rotor, the control signal can be used instead of traditional shutdown and counterweight to suppress the unbalanced vibration of the magnetically suspended rotor, as shown in this figure. Now, we talked about the result and discussions. The algorithm in this paper is used to suppress the unbalanced vibration of the rotor at the left and right magnetic bearing respectively, and the results are shown in this figure. The blue curve in the figure is the trajectory of the rotor axis before compensation, and the red curve is the trajectory of the axis after compensation. The unbalanced vibration of the maglev rotor is greatly reduced. The maximum amplitude of the rotor vibration at the left magnetic bearing is reduced by 81.4%, and the maximum amplitude of the rotor vibration at the right magnetic bearing is reduced by 77.3%. Now, let me summarize my talk. These people use electromagnetic force to try to apply control voltage to a flexible rotor supported by active magnetic bearing, instead of the traditional shutdown test and phase sensor method. Use the influence coefficient mass to detect the unbalanced quality information of the rotor with the mass unbalance and obtain the magnitude of the compensation voltage. The cross correlation mass and feedback tracking control mass in steady state is used to extract the fundamental frequency vibration signals of the rotor to obtain the phase information of the unbalanced vibration. That's all. Thank you.